A team of scientists got their data back from the James Webb Space Telescope, looked at the readout, and their collective on-the-record reaction was, quote, "What the heck is this?" Not a metaphor, not a dramatized quote for a headline. That's the actual published reaction of a planetary scientist at the Carnegie Institution, staring at data from a world that shouldn't exist under any theory. Currently, on the books, it's shaped like a lemon. Its atmosphere is made almost entirely of a substance that doesn't belong in a planetary atmosphere at all. And deep inside it, under pressure nobody can fully model yet, there may be an entire layer of diamond. Everybody, this is PSR J2322-2650b, and as of right now, it holds a genuinely rare title in modern astronomy. A planet that a team of professional scientists, publishing in a peer-reviewed journal, have stated plainly rules out every known formation mechanism currently used to explain how planets come to exist. Not one theory partially explains it. Every single one fails. And let's start with where this planet actually is, because the location alone tells you this was never going to be an ordinary world. PSR J2322-2650b orbits a pulsar, one of the strangest classes of object in the entire universe. A pulsar is what's left behind after a massive star runs out of fuel, collapses under its own gravity, and detonates in a supernova. What remains isn't a black hole, but something almost as extreme, a neutron star, an object roughly the mass of our own sun compressed down into a sphere only about the size of a city, sometimes as small as 12 miles across. University of Chicago astrophysicist Michael Jang, the study's principal investigator, described the host star in exactly those terms, calling it completely bizarre with the mass of the sun packed into the size of a city. That kind of extreme compression means a pulsar's surface gravity and magnetic field are almost incomprehensibly powerful, and many pulsars spin at genuinely staggering speeds, some completing hundreds of full rotations every single second, sweeping beams of radiation across space like a cosmic lighthouse, which is exactly how astronomers originally detect and identify them in the first place. To really appreciate how extreme that density actually is, it helps to run the numbers. A neutron star, packing roughly the mass of our entire sun into a sphere just a dozen or so miles across, means a single teaspoon of its material would weigh somewhere in the range of billions of tons here on Earth, more than the mass of every building in a major city. Combined, compressed down into a volume you could hold in your hand. That density exists because of exactly what happened during the star's original collapse. When a massive star exhausts its nuclear fuel, the outward pressure that normally holds the star up against its own gravity disappears almost instantly, and the star's core collapses inward catastrophically, crushing protons and electrons together so violently they merge into neutrons, producing an object held up not by nuclear fusion the way an ordinary star is, but by an entirely different quantum mechanical force called neutron degeneracy pressure, one of the few forces in physics capable of resisting the crushing pull of a collapsing stellar core at that scale. The outer layers of the star, meanwhile, get blasted outward in the supernova explosion itself, the violent, briefly galaxy-outshining event that first announces a neutron star's birth to the rest of the universe. PSR J2322-2650b is a planet caught orbiting one of these collapsed stellar remnants, and it's not sitting at a safe, comfortable distance either. It orbits its pulsar at a distance of roughly 1 million miles. For comparison, Earth sits about 100 million miles from our own sun, meaning this planet is orbiting its dead star roughly 100 times closer than we orbit ours. At that distance, it completes a full orbit its entire year in just 7.8 hours, something that would take Earth an entire 12 months to accomplish. This planet finishes before a typical workday is even over. That extreme proximity is directly responsible for one of the planet's most immediately strange, visually confirmed features. Researchers, by carefully modeling subtle variations in the planet's brightness as it moves through its rapid orbit, determined that the intense gravitational pull from its far more massive companion is physically stretching the planet out of a normal spherical shape, entirely distorting it into an elongated lemon-like form. Maya Belesne, a Stanford University graduate student who helped build the model responsible for confirming that shape, was part of the research team that turned subtle brightness data into an actual physical picture of a planet being pulled and stretched by gravity so intense it overpowers its own structural integrity. If a real, currently unsolved planetary mystery like this, one confirmed by actual published data rather than exaggeration, is exactly the kind of story you come here for, subscribe now, because the shape is honestly the least strange thing about this planet. Because here's where PSR J2322-2650b stops being simply an extreme gravity-warped world and becomes something scientists are describing as genuinely unprecedented. This particular pulsar planet pairing belongs to a category astronomers call a black widow system, And understanding that category is essential to understanding why this specific planet is so confusing. In a black widow system, a rapidly spinning pulsar is paired with a smaller, lower mass companion object. And over time, the pulsar's intense radiation and powerful particle wind gradually strip material away from that smaller companion, slowly consuming it, the same way the spider the system is named after consumes its mate. Researchers believe that in the earlier stages of a system like this, material actually flowed from the companion object onto the pulsar itself, which is part of what spins the pulsar up to such extraordinary rotational speeds in the first place, before the process reverses, and the pulsar begins stripping material away from its companion instead. It's a genuinely violent, long-term relationship between two objects, one slowly devouring the other across cosmic timescales. Astronomers have documented several dozen black widow systems across the galaxy since the category was first identified decades ago, and the general pattern is fairly well understood at this point. The companion object in a typical black widow system usually started out as an ordinary, if low-mass, star in a binary pairing with what would eventually become the pulsar. Over millions of years, as the pulsar's ferocious wind and radiation ablated material away from its companion, that companion star gradually shrank, sometimes down to a small fraction of its original mass. Its outer layers boiled away and blown into space, leaving behind a stripped, degraded remnant of what used to be a genuine fusion-powered star. In several previously studied black widow systems, that remnant companion has been confirmed to still be composed of roughly the kind of material you'd expect a heavily stripped ordinary star to retain, primarily hydrogen and helium, sometimes showing signs of heavier elements dredged up from deeper inside the original star as its outer layers were progressively stripped away. That established pattern is exactly what made PSR J2322-2650b's specific chemistry so jarring to the research team once they actually analyzed it. Black widow systems themselves aren't new to astronomy. Researchers have documented and studied several of them before. What makes PSR J2322-2650b different, and what makes this specific discovery so significant, is what the survivor of that violent relationship is actually made of. When researchers pointed Webb's infrared instruments at this planet and broke its light down into a detailed spectrum, they expected to find the kind of chemistry astronomers are used to seeing in exoplanet atmospheres: water, methane, carbon dioxide, the standard molecular building blocks that show up across essentially every other planetary atmosphere ever properly analyzed. That's not what they found. Instead, Zhang described the result plainly, stating that instead of the normal molecules typically expected on an exoplanet, the team detected molecular carbon specifically in two distinct forms researchers label C3 and C2, essentially small clusters of pure carbon atoms bonded directly to each other, a chemical signature that has no real precedent in the broader catalog of exoplanet atmospheres humanity has studied so far. Layered on top of that pure carbon signature, the atmosphere is dominated by helium, with dark, soot-like clouds drifting through it, giving the entire planet a genuinely alien, carbon-choked appearance, unlike anything else on record. That carbon-rich composition connects directly to the possibility that's generated so much attention around this discovery: the idea that the planet might contain actual diamond material somewhere beneath its surface. Under the kind of extreme pressure found deep inside a planet like this, researchers believe the carbon making up much of its atmosphere and interior could plausibly crystallize, forming genuine diamond, not as a metaphor or marketing hook, but as a real, physically plausible outcome of pure carbon, subjected to sufficiently intense pressure. The same basic physical process, just occurring at a scale and in an environment nothing in our own solar system remotely resembles. It's worth understanding why diamond specifically is the expected outcome of compressing pure carbon under enough pressure, because it connects this exotic, distant planet to genuinely familiar chemistry. Carbon atoms can bond together in multiple different structural arrangements, producing dramatically different materials, despite being built from the exact same element. Ordinary graphite, the soft, dark material used in pencils, consists of carbon atoms arranged in loosely stacked flat sheets that slide easily across one another. Diamond consists of those same carbon atoms instead, locked into an extremely rigid three-dimensional lattice structure, a configuration that only tends to form under very high pressure, which is exactly why natural diamonds on Earth form deep underground, roughly 100 miles beneath the surface, where pressure and temperature conditions are high enough to force carbon into that specific crystalline arrangement. Researchers have already directly confirmed roughly similar carbon crystallization processes happening inside other extreme astronomical objects, including certain white dwarf stars, the dense cooling remnants left behind by lower mass stars once they exhaust their own nuclear fuel, some of which are believed to contain enormous crystallized carbon cores, essentially planet-sized diamonds, based on detailed astro-seismological studies of how these stars vibrate and cool over time. PSR J2322. 26 in IFDB, sitting under its own extreme pressure conditions and built from an atmosphere apparently dominated by nearly pure carbon, represents a genuinely plausible candidate for a broadly similar process playing out on a planetary rather than stellar scale. Here's why all of this adds up to a genuine scientific puzzle, rather than simply an unusual but explainable planet. Zhang laid out the problem directly and clearly. If this object formed the way an ordinary planet forms, gradually assembling from a disk of gas and dust surrounding a young star, that process should never produce a world this overwhelmingly, purely carbon-rich. Normal planetary formation produces atmospheres with a much broader mix of elements and compounds, not an atmosphere apparently dominated by essentially pure carbon clusters. But the alternative explanation doesn't work cleanly either. If this planet instead represents the stripped-down remnant of what used to be an actual companion star, the more typical origin story for objects found in Black Widow systems, that explanation runs into its own serious problem, because ordinary nuclear physics, the well-understood processes governing how elements form and fuse inside stars, simply doesn't produce pure carbon in this specific way either. Zhang summarized the situation about as plainly as a scientist can. Asked whether the planet formed like a normal planet, he said no, because the composition is entirely different. Asked whether it formed through the more typical Black Widow process of a pulsar stripping down an ordinary star, he said probably not, because nuclear physics doesn't produce pure carbon that way. Every established formation pathway available to explain this specific kind of object runs into a wall the moment you actually check it against the measured chemistry. If genuinely unresolved scientific puzzles like this, the kind where published, peer-reviewed researchers are on record saying they simply don't know the answer yet, are exactly what you come here for, subscribe now, because there's an entire technical reason this discovery was even possible in the first place. And it's a genuinely clever piece of astronomical detective work. Because normally, directly studying the atmosphere of a planet this small and this faint, especially one orbiting so closely to its host star, would be nearly impossible. In the vast majority of exoplanet systems, the host star vastly outshines any orbiting planet, drowning out the planet's own faint light almost completely, and making detailed atmospheric analysis extraordinarily difficult without highly specialized indirect techniques. PSR J2322-2650b's specific situation flips that entire problem on its head, and it comes down to exactly what kind of star it orbits. Pulsars emit the overwhelming majority of their radiation as gamma rays and other extremely high-energy particles, wavelengths of light completely invisible to Webb's infrared-tuned instruments. That means, from Webb's specific point of view, the pulsar itself essentially disappears, contributing almost none of the interfering brightness that would normally overwhelm a planet's much fainter signal. Researchers can observe the planet throughout its entire orbit without its host star's glare ever getting in the way. And genuinely rare, almost paradoxical observing condition, since it means a much smaller, fainter planet effectively gets a clean, dedicated view all to itself without needing to fight past its far more massive companion's light at all. Maya Belesne described exactly what that unique setup actually enables for researchers. She explained that this specific system lets scientists view the planet fully illuminated by its host star while never actually detecting the host star itself directly, producing what she called a remarkably pristine spectrum, a clean, largely uncontaminated chemical readout that lets the research team study this particular planetary system in a level of detail that's simply unavailable for the vast majority of other known exoplanets, where a much brighter host star constantly interferes with the data. Zhang made a related point about why this kind of observation was only realistically possible using a space telescope specifically, rather than any instrument based on Earth's surface. He explained that on Earth, an enormous number of surrounding objects and surfaces are warm, and that ambient heat constantly interferes with sensitive infrared observations, since heat itself generates additional stray photons that instruments have to filter out or work around. Webb, positioned roughly 1 million miles from Earth and shielded by a sun shield specifically engineered to keep its instruments extremely cold, avoids that entire category of interference, making this kind of extraordinarily sensitive, detailed infrared measurement achievable in a way that simply, in Zhang's own words, isn't feasible from the ground under any circumstances. Roger Ramani, a Stanford University researcher and Kavli Institute scientist widely regarded as one of the world's leading experts specifically on Black Widow pulsar systems, has proposed one possible avenue toward an explanation, while being refreshingly honest about how incomplete that explanation still is. Ramani suggested that as this planet's materials slowly cooled over a long stretch of time, a mixture of carbon and oxygen within its interior could have begun to crystallize, with the pure carbon crystals that form floating upward and eventually mixing into the surrounding helium atmosphere, producing the carbon. Dominated signature Webb actually detected. But Romani was direct about the gap still sitting in the middle of that explanation. He noted that something still has to actively prevent oxygen and nitrogen from mixing into that same atmosphere alongside the carbon, since ordinary physical mixing processes would typically be expected to bring at least some of those other elements along with it, and explaining exactly what mechanism keeps that from happening remains, in his own words, a point of real, ongoing scientific controversy. Romani's closing comment on the whole situation captures the honest, genuinely curious spirit driving this entire research effort, saying plainly that it's nice not to know everything, and that he's genuinely looking forward to learning more about the weirdness of this specific atmosphere, describing it as a great puzzle to go after rather than treating the uncertainty as any kind of failure or embarrassment. That kind of open, honest uncertainty, published directly in peer-reviewed scientific literature by leading experts in the exact relevant subfield, is worth appreciating on its own terms. This isn't a mystery being manufactured or exaggerated for dramatic effect. It's genuine, documented scientific humility, researchers openly stating that a real, carefully measured phenomenon doesn't fit any of their existing models, and treating that gap as a legitimate, exciting invitation for further research, rather than something to paper over with a forced, premature explanation. There's a broader significance to this discovery that extends well past this one specific, unusual planet. Every exoplanet ever properly studied helps refine the broader models astronomers use to understand how planets in general form, evolve, and end up with the specific range of compositions we observe across the galaxy. The overwhelming majority of the roughly 6,000 confirmed exoplanets discovered so far fit reasonably well within existing, well-established formation frameworks, variations on rocky worlds, gas giants, and everything in between, produced by broadly similar physical processes, operating under different specific conditions. PSR J2322-2650b represents something genuinely different, an object that doesn't fit into any existing category cleanly enough to be explained by simply adjusting the parameters of a model that already works elsewhere. Objects like this matter enormously precisely because they reveal the current, genuine boundaries of scientific understanding, the specific places where existing theory runs out, and new physics or new formation mechanisms may actually be required to properly explain what's being observed. It's also worth understanding just how rare an observing opportunity like this genuinely is within the broader field of exoplanet science. Direct, detailed atmospheric characterization, actually breaking down a planet's light into a full chemical spectrum the way Webb managed here, remains one of the most difficult and resource-intensive techniques in the entire field, typically reserved for a comparatively small number of especially favorable, especially bright, or especially well-positioned target systems. The vast majority of the thousands of confirmed exoplanets discovered to date have never had their atmospheres directly studied in this kind of detail at all, since most orbit stars that are simply too bright relative to the planet itself for this kind of clean, interference-free spectroscopic analysis to be practical. PSR J2322-2650b's specific, almost accidental combination of circumstances, a pulsar host star that's essentially invisible to Webb's infrared instruments, paired with a planet close enough and warm enough to produce a genuinely detectable signal of its own, created exactly the rare kind of observing window that made this level of detailed chemical analysis possible at all. The research itself represents a genuinely substantial, carefully coordinated scientific effort, formally accepted for publication in the Astrophysical Journal Letters, with contributions from a team spanning multiple institutions, including the University of Chicago, Stanford University, the Carnegie Earth and Planets Laboratory, and several other research centers, all working together specifically to properly characterize this single, genuinely unprecedented object. Funding for the research came through NASA and the Heising-Simons Foundation, reflecting the kind of serious, dedicated institutional backing that goes into properly investigating a discovery significant enough to warrant this level of detailed multi-institution collaboration. So here's where this genuinely leaves us: a Jupiter-mass planet stretched into a lemon-like shape by the crushing gravity of a collapsed stellar remnant only miles across, completing an entire year in under 8 hours, wrapped in an atmosphere made of nearly pure carbon that no existing planetary formation theory can properly explain, quite possibly hiding an actual layer of diamond somewhere beneath its strange, soot-clouded surface. Every conventional explanation researchers have tried to apply, ordinary, planetary formation, the typical stripped companion star process common to other black widow systems, runs directly into a wall the moment it's checked against the planet's actual measured chemistry. That's not an exaggeration dressed up for a video title. That's the honest, direct, on-the-record assessment of the scientists who actually gathered and analyzed this data, stating plainly, in their own published words, that this world appears to rule out every known formation mechanism currently available to explain it. There's something genuinely valuable in a discovery like this beyond the specific puzzle of one unusual planet. Science generally advances fastest, not when every observation neatly confirms what researchers already expected, but precisely when something like PSR J2322-2650b turns up, an object that stubbornly refuses to fit any existing model, forcing genuinely talented, experienced researchers to admit, on the record, in a peer-reviewed journal, that they don't yet have a satisfying answer. Peter Gau's blunt, immediate reaction upon first seeing the data, simply asking what the heck this thing actually was, and Roger Romani's genuine enthusiasm about having a real puzzle worth chasing, both capture something true about how science actually progresses. The gaps in understanding, honestly acknowledged rather than papered over, are usually exactly where the next genuine breakthrough ends up coming from. If genuinely strange, genuinely unresolved discoveries like this, the kind where leading experts openly admit they don't have the answer yet, are exactly the sort of real science you come here for. Subscribe and turn on notifications, because Roger Romani and the rest of this research team are already working on the next piece of this puzzle, and we'll bring you their answer the moment they actually find one.